First Tech Challenge challenges kids ages 12 to 18 to program, design, build, and compete with robots.
First Tech Challenge is one of 3 engaging first.
Here they release a new challenge.
Once you get the challenge, you figure out your game plan.
Teams use a reusable kit to program robots in a variety of coding languages.
Every year you also learn more and more about coding, so then your code's gonna get better and better.
Personally, I do not learn hearing about it, but hands-on is just go into it. Instead of saying, oh, I know how to build this robot, I can say, I built this robot.
In First Tech Challenge, students are developing a broad range of skills.
Manufacturing, hardware, troubleshooting, but there's also a lot of things that you learn that you wouldn't necessarily think about. People skills.
Problem-solving skills, helping one another, helping other teams.
The program draws so many students that come in who just want to do the marketing, who just want to do fundraising. And that's a great thing that the kids learn very early on.
The model of FIRST has provided incredible opportunities for the students to interact with professionals.
Whenever I asked my mentors the question, they always flipped the question around and asked, where would you find the answer to that question if I weren't here? They slowly built my confidence up so much more to a point where we weren't asking them questions, we were just going.
Each team has to compete at a local event, win awards at the local event, and then they're able to move on to the first championship.
You walk into the room and there's that smell. The smell of robots.
3, 2, 1, There's different languages, different culture. It's just the best thing ever.
There are scholarships for colleges, universities, as well as technical programs.
I think it's incredibly important for youth to see careers in science and engineering as a possibility for them.
First Tech Challenge is like an avenue for me to express my creativity with like-minded individuals that later become my friends through the program.
First in one word, wow.
Fun!
First is inspiration.
First is amazing.
First is hope.
Okay, so yes, first is amazing and amazing. Good morning to everyone. I know that each of you is really waiting for this live session about this First Tech Challenge training brought to you by Felta Multimedia Incorporated, the national organizer of First Lego League Philippines and Philippine Robotics Olympiad Competition, which will be branded World Robot Olympiad Philippines this 2026. Okay, so if you are watching live right now, I know that most of you are really waiting for this session. Please share this live video to your friend, to your teachers, to your coaches, to your school admin, to your friends, and even to your family so that they know what is the wonders that we could get in robotics. Okay, and if you are watching live right now, please comment down your school name or your robotics group name and share us your location as well so that we are aware where you're coming from, and we could also witness that there are so many youth nowadays who really wanted to embrace the magic of robotics through science, technology, engineering, and mathematics. Okay, so what are you waiting for? Share this live video. As you could see from my slide, we have so many topics that we're gonna discuss this morning so that you will be more aware of what is First Tech Challenge, what are those things that you need to prepare ahead of time, what are those things that you need to fully understand before you embrace the challenge of First Tech Challenge. So what are you waiting for? Ayan, share nyo na yung live video so that there will be more schools who will be aware that there's this new program that Felta Multimedia Inc. wishes to offer here in the Philippines. Of course, we wish to level up. Okay. Okay. Sige, ano lang, we really wanted to conduct this introductory training so that we could reach more people. Even though that you have your prior commitment today, we intended to showcase this live training live so that later on you could watch the recording, you could review the recording, you could share it to your friends, you could share it to your group mates so that you are aware that there are new programs that we wanted to share with you, especially for our youth. Okay, so again, welcome to our first tech challenge training. Okay, this is our second session, and last session we able to share with you of what is first tech challenge, why do we wanted to embrace FTC here in the Philippines? What are those things that we need to have? What are those things that we need to clearly understand? And specifically last session we able to share with you what are the specific items that we need to have and what are those pieces inside the box, what are the functionality of those pieces inside the box. But for this training session, it will be more in depth. Okay, for we will be exploring on how we gonna do and manage the control system, how we gonna do the component configuration, how do we program from basic up to competition blocks, the controller, the autonomous mode, the basic robot movements as well. All right. So what are you waiting for? Ayan, meron na tayong mga viewers who are with us at the moment. So share niyo na po yung video natin because we wanted to reach out our youngster from Luzon, from Visayas, and from Mindanao. Okay, so you might be wondering why we are embracing this FTC in the Philippines during the season of World Robot Olympiad Philippines. Okay, since this is our kick-off for this FTC, no, makakasama po siya as part of our activity sa darating na 2024 Philippine Robotics Olympiad Competition na magaganap po this June 22, June 23, June 24, and June 25 sa SM Mall of Asia. Okay, so magiging parte po ito ng ating activity sa parating na Philippine Robotics Olympiad Competition as exhibition game. So if you think you really wanted to level up and if you think you really wanted to embrace this program, please join our live session, okay? And then we are inviting you as well to join us sa parating po na Philippine Robotics Olympiad competition. So if you are watching, please share this live video. Okay, so checking out the comment section because if there's anything that you wanted to ask, if there's anything that you're curious about, you could always use our comment section, and there are technical people who will be very happy to assist you. All right. Okay, so I guess we are all set to begin. Okay, so to officially begin, of course, good morning again to everyone and welcome to our first Tech Challenge training. Okay, and the main focus of this training session is black coding and robot control, proudly hosted by Felta in partnership with First, of course. And I'm Teacher Ann. I am your facilitator for today's live session. Okay, so I will be around to facilitate and help our instructor in charge for this training session. And of course, we're very happy and excited to have all of you here. So this training session is welcome for students, for teachers, for coaches, even for parents, so that they will be aware of what are the programs that we are planning to have in First Tech Challenge and the future innovators and for the enthusiasts as well. So please watch and enjoy the sessions. And for today's session is it's part of our continuing mission to introduce our learners to the exciting world of robotics, coding, engineering, and innovation through hands-on and interactive learning experiences. So, before we begin, just a little recap, just for those who just tune in and watching at the moment. So, before we begin, let's first understand what is First Tech Challenge or FTC is all about. I believe that we've shared that already last session. Just to highlight and emphasize again, the First Tech Challenge is an international robotics competition that is definitely designed for students to learn and apply skills in science, in technology, in engineering, in mathematics, also known as STEM. So that's the main goal, that's the main purpose. Use robotics in innovation, enable for us to escalate our STEM programs in academe. Okay? So technically, in First Tech Challenge, student work in teams. So they gonna design robot, they gonna build robot, they gonna program robots, they gonna solve real world engineering challenges, and as well as they will compete in exciting robotics games and missions. But in First Tech Challenge, it's more than just building robot. Okay, I wanted to emphasize that its main goal is, of course, is to inspire young people to become creative thinkers, to become problem solvers, to become team players, and to become future innovators and future leaders. So, talking about First Tech Challenge, technically and definitely it will help our student to develop not only the technical skills in robotics and coding but also important life skills such as collaboration, communication skills, critical thinking skills, creativity, leadership, and confidence. So these FTC programs will definitely encourage our learners to learn by doing things, turning ideas into actual working robots and solutions. So, one of the best thing about First Tech Challenge is that students experience real-world engineering practices in a fun and a very engaging way. So, First Tech Challenge definitely gives the learners the opportunity to explore coding and programming, understand robotic system, experience teamwork and collaboration, and develop innovation and their problem solving skills. So by all means, it will prepare for their future careers in technology and engineering. And through training like this, a student can definitely discover their passion for robotics and technology while they are enjoying the process of learning. So before we officially move in Sorry for that. Okay, before we officially move in for today's topic, let's have a short recap of our previous session last Saturday. So, last Saturday, we focused with what are the specific hardware or materials that we need to have enable for us to join FTC competition. So specifically, we explore what inside the box because it's very important for us to clearly understand what is the program about, what is the goal of the program, what is the mission all about, and what are those necessary things that we need to prepare prior joining and embracing the challenges. So we started exploring what's inside the box. We explored the different component included in the FTC robotics kit and learn their function. But technically, we will be more in-depth for today's session. So last time, we able to share with you and we've discussed important robot parts such as its controller, its motors, the wheels, the sensor, the control hub, the battery cables, and the structural parts and the connector. So last time, we also learned how each component contributes to the movement, to the control, and to the overall performance of all the robots. So technically, understanding these materials is very important, especially if you are new to the program, because it will contribute to the movement, to the control, and to the overall performance of the robot. So understanding these materials is very important to us because before we code or control our robot, of course, we first need to understand the parts that make the robot works. Since this is our kickoff activity for this FTC program. Now, moving forward, we are now ready for the next exciting step in our FTC robotics journey, black coding and robot control. So, as you could see from my slide, we have there our key topics. So today we will definitely explore the control system. We can explore the components configuration, the FTC programming basic for now, the teleop control, the autonomous mode, and the basic robot movements. So as we continue, please feel free to participate in the comment section. You could always ask questions and you can interact with us throughout the session. And remember, learning robotics is more fun when we explore and discover together. So, without further ado, let's begin our first tech challenge training on black coding and robot control to be led by our FTC instructor, teacher Jury. Hello, Sir Jury.
Hello.
Hello. So, are you ready, sir?
Yes, I am ready.
All
I'm
right,
ready.
all right. So, teacher Jury, last session you able to thoroughly discuss of what are the materials needed for this FTC competition. So, I believe for this training session, we will now be more exploring on how we could control, right?
Yes, that's right. That is right. That is
Okay,
right.
so yes, we're all excited. So, without further ado, we'll be giving the spotlight to you. Good luck.
Thank you, Miss Anne. So first, let me share my screen to you guys. Okay. So for today's lesson, uh, before we start, let me introduce myself. Good morning, everyone. Welcome to today's session. My name is Jury, Sir Teacher Jury, Salvador Estoriano, and we're going to spend the next hour together on one of the most exciting parts in the FTC coaching training series, which is the block coding and robot control. So I want to open with the quote on this side. By first, we don't use kids to build robots, we use robots to build kids. Read that again and let it sink in, because what we are really doing here today is not just learning how to make robots move. We are learning how to use that robot as the vehicle for developing something far more important: the minds and characters for young people in your care. When a student writes their first line of code, the robot moves for the first time. Something happens to that student. They realize that their thinking, their logic, their ideas can have a physical effect on the world. That is a transformative moment. As coaches, we are the people who set up the conditions for that moment to happen. Everything we cover today is in service of that goal. Let's dive in. Our session is titled Block Coding, the Robot Control. We will work through five major topic areas: control system, components configuration, FTC programming basics, teleop control, autonomous mode, and basic robot movements. By the end of the day, you will have a complete picture of how a robot receives its instructions and how to give your students through writing those instructions themselves. So let's move on to the keynotes or the agenda for today. Before we go deeper, let's preview today's roadmap. The six topics listed here are control systems. I will repeat again: control systems, components configuration, FTC programming basics, teleop control, autonomous mode, and basic robot movements. These are not independent topics, they are layers. Each one builds directly on the previous one. Control systems establishes the hardware foundation, what is the brain of the robot, and what does it actually do. Components configuration is the bridge. We will tell the software what hardware is connected, and we assign names that the code will use. In FTC Programming Basics sets up the environment and tools your students will work in every session. Teleop and autonomous mode are the two programming paradigms, human-controlled and self-controlled. And lastly, basic robot movements. Movements grounds everything in the physics of how motors produce motion. I want to give you a coaching principle right now that applies to every topic we discussed today. Always check for foundational understanding before advancing to the next layer. If the student does not know which port their motor is plugged into, their code will not make sense to them, even if the syntax is correct. Coaching this material is as much as about diagnosing gaps in the foundation as it is about teaching new content. Keep that lens active throughout today's session. So let's move on to the control systems. This covers the hardware brain of the FTC robot, specifically the Rev Control Hub, and the role it plays in everything the robot does. And it plays everything the robot does. A coach who deeply understands a control hub is a coach who can troubleshoot almost anything that goes wrong on the robot. Because every robot, every servo, every sensor, every line of code ultimately flows through this one device. So, what is the Rev Control Hub? Rev Control Hub is described as the slide as the main brain of an FTC robot. It also the proud supporter of FIRST. That is it is accurate, but let me unpack it so that when you explain this to your student, you have a richer mental model than just the phrase. Physically, the control hub is a compact rectangular board about the size of a thick smartphone that mounts directly onto the robot's frame. Do not let the size fool you. Inside is a real embedded computer, a quad-core ARM processor, 1 gigabyte of RAM, 8 gigabytes of storage, running an Android-based operating system. This is not a toy controller. It is a capable of computing platform that was designed and packaged specifically for educational robotics. And it runs real software that your students write. The control hub performs 5 distinct roles simultaneously. I want you to be able to name all 5. First, it is the robot controller computer. It executes the op mode programs your students write in real time during competition. Second, it is a reading their encoder feedback. Third, it provides sensor interfaces. It has ports for digital sensors, analog sensors, and I2C sensors, allowing the robot to sense its environment. Fourth, it handles wireless communication. It broadcasts its own Wi-Fi network that the driver station app and the Rev hardware client connect to. And fifth, it manages power, distributing and regulating voltage from battery to all connected components. Here is something that surprises many new coaches and students. The control hub does not connect to your school's Wi-Fi. It creates its own Wi-Fi network. The driver station phone connects to that network. The programming laptop connects to that network. They are all talking to each other through the robot's own private wireless system, completely independent of any external internet connection. At competitions venue, where dozens of robots are operating simultaneously, each team has their own isolated network. Where dozens of robots are isolated network. That is what prevents one team robots from accidentally receiving another team's commands. From a coaching perspective, the five-in-one nature of a control hub is both a strength and a teaching challenge. The strength: one device controls the whole robot. The challenge: if that one device is misconfigured, not updated, or physically damaged, nothing works. Emphasize early that the control hub is critically infrastructure. It should mounted securely, protected from impacts, and kept updated throughout the season. So, what components can you connect to the control hub? Let's talk about what connects to it. This slide organizes connection into four categories: actuators, inputs, battery, and data. Actuators are the output devices, the components that produce motion. DC motors, like this one I'm holding, and servo motors connects to the hub actuator ports. When a code says set motor power to 0.5, the hub translates that instruction into real electrical signal that drives the motor to have power. Without the correctly connected and configured actuator, that instruction produces nothing. The code runs, but the robot still sits still. Understanding this end-to-end chain is important for troubleshooting. Inputs are the sensors and feedback devices. Encoders, built into Maverick motors, continuously count shaft rotations and report back to the hub. This is what makes the robot know how far it has traveled. External sensors such as color sensors, distance sensors, and touch sensors also connected here, giving the robot additional awareness of its environment. The control hub also has a built-in IMU, an inertial measurement unit, that measures orientation and rotation without any external sensor. That built-in IMU is extremely valuable for autonomous programming. The battery is a power source. The 12-volt NIF pack connects directly to the hub's power input. Everything downstream, motors, servos, the hub's own processors, runs on energy provided throughout the connection. A low or disconnected battery affects the entire system, and battery management is a routine operational skill for teams needed to develop early. Data connections allow configuration and updates. The USB ports connect to a laptop running the Rev hardware client or firmware updates and diagnostics. The RS485 port connects to an optional expansion hub when more motor or server ports are needed. For most starter board operations, the primary data connection is the Wi-Fi link used for programming and telemetry. So let's move on to the parts of the rev control, or the port reference diagram. This diagram is one of the most practically important reference in today's entire session. I strongly recommend that coaches print this diagram and post it in their build space. Students will need to refer to it constantly during both the hardware build phase and the software configuration phase. Let's walk around the diagram systematically. On the left side of the hub, we have the motor and encoder ports. Four of them, numbered 0 through 3. DC motors plug in here. The encoder cables from each motor, the thin cables that carry rotation count data, also terminate at these ports. The port number you used here becomes the foundation of your software configuration when you create the configuration file. You will assign a name to each port number. That name must be used exactly in your code. Along the bottom edge, we have servo ports. 6 of them, numbered 0 through 5, with a 5-volt power trail alongside them. Servos connect here. Unlike motor ports, servo ports do not carry encoder feedback. Servos are controlled by position signals, not by shaft counting. On the right side, we have expansion ports at the top, allow you to chain an additional expansion hub for more ports. Below that are the sensor ports, divided into digital ports for simple binary sensors, analog ports for variable signal sensors, and I2C ports for more complex sensors. The letters I2C stands for Inter-Integrated Circuit. This control supports sensors like a color distance sensor and the built-in IMU. At the top left, the battery input connector. At the top right, are the UART and USB connections, along with the power button, and the status LED. That status LED is the first diagnostic tool. Blue means booting, green means ready. A flashing pattern means something needs attention. Here's a coaching exercise I highly recommend. Before your students write a single line of code, sit down with this diagram and physically trace every wire on the assembled robot from its component back to its port. A student who can look at any motor on the robot and says that that is the left drive motor. It is on port 0, and it is named left motor in the configuration. And my code uses the exact name, has a complete mental model of the hardware-software chain. That mental model is what makes troubleshooting possible. Now let's move on to the technical specifications of the Rev Control Hub. This slide lists the technical specifications of the Control Hub. You do not need to memorize these, but I want to highlight a few that have practical implications for coaching. So the Rev Control Hub has a processor of an RK3328 quad-core ARM Cortex A53. This is the same class of processor used in budgets Android phones. For the scale of FTC program, this is more than adequate. The processor is never the performance bottleneck. When students say their code is running too slow, the cause is almost always logical errors or inefficient loop structure, not hardware limitations. The Android-based operating system is important context for understanding why FTC programming tools work the way they do. The blocks editor and the onboard Java both run in web browser hosted by the control hub itself. You access them by navigating to a specific IP address on the hub's Wi-Fi network. This means your programming laptop does not need any special software installed, just the web browser. The Rev hardware client is the only desktop application needed. The Wi-Fi specifications 802.11 AC/B/G/N supports both 2.4 GHz and 5 GHz frequencies. At competition venues with many teams, the 2.4 GHz band can become congested, causing connections instability. FTC has rules about which Wi-Fi channels teams may use, and the Rev hardware client allows you to change the hub's broadcast channel. Configuring Wi-Fi channel is one of the pre-competition maintenance tasks that experienced teams know to perform. So the power input ranges to 8 to 15 volts, accommodates the 12-volt NIMF battery while tolerating normal voltage fluctuations. The hub's weight of approximately 209 grams is negligible in the context of the full robot build. So here's as we demonstrate live. I want to highlight 4 specific things to observe. First, watch how the motor's cable's JST-VH connector sits into the motor port. It clicks when fully inserted. That click is not just satisfying, it is diagnostic. If there's no click, the connector is not fully seated, and the connection may be intermittent. Intermittent connections are one of the most frustrating sources of the robot misbehavior during practice, because the robot works sometimes and it fails other times with no obvious cause. Always click check motor connections before every run. Second, watch the servo other times connections before every one. So let's move on to the components configuration. This is the bridge between hardware and software, the step where you formally tell the control hub what is physically connected to it, and what each component will be called. Without this step, code cannot communicate with hardware. Configuration is not programming, but it is just as critical as programming. And mistakes here produce errors and look like programming bugs. So let's meet the FTC Driver Station app. FTC Driver Station is the official application used to control and monitor the robot during matches. It runs on a dedicated Android phone or tablet. Separate the control hub and communicates wirelessly over the hub's Wi-Fi network. The driver station serves four distinct functions and that coaches need to understand well. The first is operator interface. During teleop, the two gamepad controllers plug into the driver station device via USB, and the driver station relays every joystick movement and button pressed to the control hub in the real time. Every motion the robot makes during teleop originates as the physical controller input that flows through the driver station. The second function is program selection and match control. Before a match, the drive team used the driver station to select an op mode, which robot program. Op mode means operation mode, which robot they want to run. They choose between autonomous and teleop mode, initialize the selected program, and then start the robot at the match signal. Match signal. Getting the sequence correct under time pressure at competition is a skill that requires dedicated practice. Many teams lose precious seconds fumbling with the driver station during the match countdown. Include driver station operation drills in your regular practice routine. The third function is the telemetry display. When your students add telemetry lines to their code, instructions that send data values to the driver station screen. That information appears in the real time during operation. Telemetry display when you students add telemetry is your primary sorry telemetry is your primary debugging tool, logging the encoder count, the battery voltage, the servo position, or any other value lets you understand exactly what the robot is doing internally, even when you cannot see the physical components directly. The fourth function is the system health monitoring. The driver station continuously display battery voltage, Wi-Fi signal strength, ping time, and overall connection health. Training your students to check these indicators before everyone catches problem early. A low battery or a high ping before practice run is easy to fix. The same problem discovered mid-match is a disaster. A maintenance note. The driver's station updates regularly. Make sure your driver always running on the same software version as your control hub. Version mismatches between the driver station and the control hub cause communication failure that are difficult to diagnose if you do not know to look for them. Version synchronization is the start of season and pre-competition task for experienced teams. Now let's move on to the parts or deep dive more into the parts of the FTC Driver Station app. So at the very top of the screen is the driver station name, shown here as the 1234RC. This is the name of the control hub the driver station is paired with. At competition venues, many teams operate simultaneously. If this name does not match your robot, you are connected to someone else's robot. This is more common than you would expect at the larger events. Always verify the driver station name before initializing any program. Directly below is the battery percentage for the driver station device itself. The phone or tablet's own battery, not the robot's battery. A driver station that dies during a match is entirely preventable. Charge it before you practice and every competition. The user 1 and user 2 indicators are on the right side shows whether the two gamepads are registered and recognized. A blank indicator means the controller is not connected. Always verifying both gamepad indicators before match start. A drive team that begins a match with an unregistered controller has no way to control the function during the entire 2-minute period. The middle section displays the network name, the hub's Wi-Fi SSID, and the ping value. Ping is the rounded-trip communication delay in milliseconds. A value of 3 ms, as shown here, is excellent. Above 20 milliseconds, you may notice slight control lag. Above 100 ms, the robots will feel unresponsive. In environments with Wi-Fi congestion, monitor this value and change the hub's Wi-Fi channel if needed. The battery voltage indicator below the network section shows the robot's battery real-time voltage. A healthy, fully charged 12-volt NIM battery reads between 12.6 and 13 volts. Below 11.5 volts, motors begins running noticeably slower. Before 10.5 volts, behavior becomes unpredictable. Train your students to call out voltage before each run to swap batteries proactively. Never wait for a failure. The mode configuration The mode configuration section is where the drive team selects which op mode to run and toggles between autonomous and teleop. The large init button initializes the selected program setup phase. After initialization succeeds, a start button becomes available. The status bar at the very bottom confirms the current robot state. So let's move on to how do you create a configuration file. Creating a configuration file is a critically first step before any robot can function. This is where you tell the control hub formally and precisely what is physically connected to it, and what each component's software name is. Without the configuration file, the hub has no inventory of its hardware, and code that attempts to use a motor or servo will fail immediately with a hardware not found error. The configuration is created inside the FTC Driver Station app. From the main screen, tap the three-dot menu at the top right, select Configure Robot, and you will see the list of existing configurations and a new button to create one. When you create the new configuration, the app scans the connected hub and presents each port for you to define. You select the device type for each occupied port: DC motor, servo, color sensor, and so on, and then you assign a name. The name is the contract between your hardware and your code. Whatever the name you assign to a motor in the configuration must be used exactly. Exact spelling, exact capitalization every time that the motor is referenced in the code. If the configuration names the left drive motor left motor, but the code says left motor with a capital L, the code will crash. If the configuration says left motor with an underscore, but the code says left motor as a one word, the code will crash also. This name matching requirement is one of the most common sources of beginner errors, and the fix is always the same. Check the configuration, find the exact name, copy it precisely into the code. Before building the configuration and before writing any code, I recommend establishing a naming document. Just a simple, just like a Word or a Microsoft Word, you can simply share the reference that lists every hardware component, its port number, and its configuration name. That document becomes the ground truth for both the configuration setup and all code written by all students on the team. Consistency eliminates a whole category of errors. For StarterBot, the configurations use the following assignments. For motors, left motor on port 0, right motor on port 1, flywheel motor on port 2. For servos, backspin servo on port 0, right servo on port 1 and left servo on port 2. These names will appear in the code examples we'll examine later today, and you will see exactly how the configurations name bridges the hardware's and the software worlds. Once the configuration is built, tap Activate to make it active configuration. Only one configuration can be active at a time. Verify the active configuration name appears in the driver station network section before running any programs. So let's move on to the hardware configuration. Let's trace the physical power path through the robot, because understanding this chain is as important for safety as it for troubleshooting. The connection sequence is: battery connects to the on and off switch. The switch connects to the rev control hub. Every component on the robot, all motors, all servos, all sensors, the hub's processor itself draws the power itself through this chain. The switch is a single, immediate point of control for the entire robot's electrical system. FTC rules require every robot to have an easily accessible, clearly identifiable power switch. The purpose is safety. At any moment during practice or competition, a runaway robot or a software crash, a mechanical failure, any adult or referee must be able to cut power to the robot immediately without reaching into the robot's moving parts. Make sure your switch is positioned accessibly, and make sure every student on your team knows exactly where it is and how to use it quickly. The connection uses Anderson power pole connectors, the distinctive spring-loaded, color-coded connectors you see in the diagram. Red is positive, so red is positive, and black is the negative. Black is the negative. These connectors are designed to be keyed against reversal, but verify polarity on the new wiring before power on for the first time. A reverse polarity connection to the hub can damage the electronics. When in doubt, check with a multimeter before connecting a power. A practical coaching tip on the battery management. Label each battery with its team number or unique identifier and label the battery slot on each robot. A shared pool of unlabeled batteries is a logistics problem and that experienced teams solved early. Knowing which batteries are charged, which needs charging, and which belong to which robot prevents the practice session disrupts or of discovering a dead battery right when you are ready to run. Next is the servo port assignments. Starting with the servo connections. Three servos are used in this design. The backspin servo is connected to servo port 0, the right feed servo is on the servo port 1, and the left feed servo is on the port 2. These three servos control the ball feeding mechanism. The backspin servo provides backspin to game elements as they enter the shooter system, stabilizing their flight trajectory. The right and left feed servos act as a gate. Their angular position determines whether the robot is actively feeding game elements into the shooter or holding them in the stage position. The coordination of these three servos determines the robot's scoring effectiveness. For students programming servos for the first time, the key concept to introduce is the servo's positions value. In FTC block code, servo's positions are decimal values from 0 to 1. The value 0.0 represents one extreme of the servo's range. 1.0 represents the other extreme, and 0.5 centers the servo. The exact position values that corresponds to gate open and gate closed. For this specific mechanisms are determined through testing. There's no shortcut. Student must set a value, run the program, observe the physical position, and adjust until the mechanism works as intended. A critical coaching habit to instill: every time a servo positions value is calibrated and confirmed to work. Write down immediately. Calibration values that exist only in the student's memory are lost the moment that students goes home. Calibration data belongs in the engineering notebook before the practice session ends. Now for the DC motor. The motor port assignments for the starter pot are left drive DC motor on port 0, right drive DC motor on port 1, and the flywheel DC motor on port 2. The two drive motors on port 0 and 1 uses a 50.9 to 1 Maverick motors. The high gear reduction provides the torque needed to drive the robot's weight across the field efficiently. The flywheel motor on port 2 uses a 3.7 to 1 ratio. The fast gear ratio because the flywheel needs to high rotational speed to launch the game elements at the competition level velocity. There is an important nuance about the drive motors that can sorry mirror image of each other on the robot frame. This means when you apply the same positive value on the both motors, one motor's physically forward direction is the other motor's backward direction. One motor will drive the robot forward while the other drives it backward, and the robot will spin in a circle. This fix is not in the wiring. The fix is in the code. During the initialization phase of your op mode, you set one motor's direction to reverse so that the positive value commands the motor to spin in the physically forward direction. From that point on, your positive power forward is the true for both motors. The drive the drive code becomes consistent and predictable. If your students see the robot spinning in a tight circle where they expect straight line driving, a missing motor reversal is the first thing to check. Understanding Understanding this is not just a coding trick, it reflects a real concept in mechanical engineering called symmetric mounting, where identical components are installed in mirror image orientations to achieve structural balance. Connecting the physical observation to engineering concept is the kind of deeper teaching in that FTC makes possible. So let's move on to the FTC programming basics. Our third section is FTC programming basics. This covers the programming environment your students will use, the tools available to them, then the workflow of writing code to running it on the robot. This section establishes the vocabulary and workflow that our teleop and autonomous discussion will depend on. So this is what the robot should look like when you finish building the starter bot using the FTC Studica kit robot. The robot sits on four specialized wheels. These are mecanum wheels, identifiable by the angled rollers around their perimeter. A mecanum wheel drivetrain can theoretically move in any direction, including sideways, by varying the speed and direction of individual wheels independently. For the initial starter bot code, we used a simpler tank drive control scheme, but the mechanical capability for more complex movement is present in the hardware. On the top of the drive base, an open aluminum frame structure houses the ball shooter. Two spinning flex wheels powered by the flywheel motor from the form motor form the shooter. The game elements fed between these spinning wheels are launched outward at speed. The three servos we discussed in the configuration section control that feed gates that manage the flow of the game elements from the intake area into the shooter path. From a programming's perspective, controlling this robot means simultaneously managing two drive motors for locomotion, one flywheel motor for shooting, and the three servos for feeding, all coordinated in response to either driver inputs in teleop or a pre-written sequence in autonomous. This is not trivial, helping students organize their code into logical subsystems, drive, shooter, feed, and even when writing in blocks, produces more readable, debuggable programs than a single unstructured sequence of blocks. So let's move on to the Rev hardware client. Before your students can deploy to the robot, your team's laptop needs the Rev hardware client installed. This is a Windows desktop application available at the link on this slide. The Rev hardware client serves three primary functions. First, firmware updates. It detects the connected control hub and allows you to update its firmware to the latest version in a few clicks. Running updated firmware is one of the most common causes of mysterious robot behavior that is difficult to diagnose. Unexpected crashes, communication instability, features that do not behave as documented. At the start of every season, firmware update is one of the first tasks on your team setup checklist. Second, hardware configuration from a computer. While configuration can be also done with the Driver Station app on the phone. The hardware client provides a more comfortable interface on the laptop screen, especially for first-time configuration. Third, diagnostics. The hardware client shows detailed information about connected devices, port status, and system's health. When something is not working, you cannot figure out why. Connecting to a hardware client offers reveals the cause quickly. Okay, sorry for the lag. Third, the hardware client connects to the in two ways: via USB when the hub is connected directly to the laptop. This is preferred for firmware updates because it is faster and more reliable for larger transfers. Via Wi-Fi when the laptop is connected to the hub's wireless network. This is convenient for wireless diagnostics during practice without cabling the robot. So next one, connecting the hub to the Rev hardware client. These slides walk through the step-by-step process of powering the control hub and connecting it to the Rev hardware client. This is a procedure your students will repeat at the start of every programming session. So step 1. Power on the control hub using the robot's on and off switch. Locate the toggle switch on the robot's frame, the one connected between the battery and the hub. Flip it and on the position. Step 2. Observe the status LED on the control hub immediately after switching on. The LED glows blue. This indicates the hub is booting, the Android OS is loading, the Wi-Fi radio is initializing, and the FTC robot controller application is starting up. This process takes 15 to 30 seconds depending on the hub state. Do not attempt to connect during the blue phase Wi-Fi network is not yet available. Step 3. When the LED transitions to green, the hub is fully ready. Green means the Wi-Fi network is broadcasting and the robot controller is running. At this point, open the Wi-Fi settings on your laptop and look for the hub's SSID. A network name includes the hub serial number or team assigned name. Connect your laptop to that network. Once the laptop is connected to the hub's Wi-Fi network, the Rev hardware client will automatically detect the hub and display it in the connected hardware list, just like in this slide. One important competition note: at the events of many teams, many hubs will be broadcasting simultaneously. Make sure your students connect their own robot SIT, naming the hub clearly during initial setup. Using this Using your team number or robot name prevents accidental connection to a neighbor's robot. The hub's network name can be changed throughout the Rev hardware client under the networks for the device. So step 4, after you click the control hub in the Rev hardware client, it will lead you to the configuration of the hub. You need For this part, we need to go to the program and manage to show the robot controller console. Next one, go to the blocks tab and it will lead you to the op mode lists. To create an op mode, just click the create new op mode. With that, a a modal will appear, and then you can type the op mode name, and also and after you put your op mode name, you can select the basic op mode for this session. After that, it will lead you to the interface of the blocks. So for this session, we will use the blocks coding. So as you can see, we have a program area. As you can see, we have a program area that you can visualize the blocks, the if some of the blocks, control blocks, and the motor blocks. On the left side, we have the blocks. We have a linear op mode, just like in this example. To run op mode, to run op mode is like a function. Then a gamepad block. If you use a teleop mode for the gamepads, actuators for DC motors and servo motors and other output output components, sensors, and then we have a sensors. Sorry for the lag, for the internet connectivity. Sensors for the ultrasonic sensor, and I also the IMU, also the other devices, or and then also the androids and utilities. So below that, we have a blocks logical um, if blocks, or I mean if blocks, or a conditional statement blocks. Loops is where you use a continuous running what inside the block. Math for operational, arithmetic. Text for comments or used to label the blocks so that you can keep track each block or each function so that you cannot log Sorry for the internet connectivity issues. So let me share screen again my slide. Okay. Okay, we can hope we can continue. Let's continue the for the Rev hardware client. So variables you can so again the blocks on the left side of the box we have logic for the conditional statement like ifs, if else statement, or the condition. For example, in this code, if call up mode is active, it will run what's inside that block. Next, we have a loops. It is a from the name itself, continuous running, or you can set the condition. For example, repeat while up mode is active. So what's inside it will continuously run until interrupted. Next, the math blocks is used for operational statement. For example, like in the movements or the value of the movements, you can make it negative value or positive value depending on the program that you want to use. Text is used for comments. For example, comments just like in the top here, put initialization box here. That is a text that you can use to use a label for managing codes so that you can keep tracking and not lost when your code becomes becomes complex. List is for something that you can use to list, I guess, value. For that value, if you have a more data that you want to output or use for the code. But for this specifically session, we just need to use a basic programming. So variables you can use for initializing value, initializing setup, first initialization of the value. For example, you can create a variable for speed, and then you can set the value for it, and you can use that variable so that it's organized, and you can name it depending on what you want to use. For example, speed, or motor power, or the time, or how much your motors will run. And then let's skip the miscellaneous part. So yeah, there's the client overview. Again, the left side is for the code blocks. This big part, white part, is the programming area, and then it has also uh, a a copy for the Java code, or the what it looks like on Java. For example, this is the block code, and then in Java, this is what it looks like. What you have block code on the programming area, and then on this part, on this bar, we have the up mode name. You can see this the basic movements, and then the mode on the up mode. In this drop down, we have tele up mode and autonomous mode. In this part, you can save the up mode, export to Java, download up mode. Download up mode means you download the code from the Rev hardware client through the Rev control hub. And then you can also in some coding. Oh, okay. Let me repeat it again. So to run up mode or the wrapper is like a function block or a function in other programming, but in this block in the Rev hardware client, it's called the wrapper. It is what it will run. Let's read this. What it does, it tells the robot brain everything inside this block is what you should execute when I select this program on the driver station. For example, the name is practice autonomous, and it's just the label you gave this specific set of instructions. So it will run the run up mode when you hit the play button after you click the init button in the driver station app. Next one is I created a is the value is the variable. So I created a variable called speed and set the value to 0.5. So which means a 50% power. Using a variable is smart if you decide the robot is moving too fast. Later you only have to change this non-number instead of changing it ever in the code. So instead of giving a value in each motor, you can create a variable and set the value for it and connect the variable to the motor. So when you want to make it faster robot, you just only need to change the variable that you set on the initialization part. Next is the call wait for start. This is very important in the block coding because when you click in the driver station app, when you click the init button, if you don't have a wait for start, the motors will automatically run. So you have to put a call wait for start block so that when you click the init button on the phone, it will not run the motors immediately. Instead, you have a play button, and then when you hit the play button, that's when the motors will run. So here's an example of the move forward. A while ago, in the DC motor configuration and the starter bot, the motor for the left and right is not the same rotation. So in here, right motor 0 power is equals to speed of 0.5. So it is a positive rotation. Then the left motor in the port 1, it has a negative speed, so when the motors run, it will move forward and not turn. It will not turn on its place. And then the call sleep is just uh, a time for the how many seconds or how much longer the motor will speed. Also, you need to set the right and the motors to 0 so that it will it will it will call the sleep. So because if you do not put a value of zero powers the motor to 0, it will just ignore the call sleep and it will move the robot infinitely or continuously. If you put the motors to 0, the right and left to 0, after the call sleep, it will just time the movement. For example, if you put 1000, it is 1 second movement. Now let's move on the teleop control. So we are now enter our fourth section is the teleop control. Teleop, short for teleoperated, is the phase of an FTC match where the human drivers control the robot in a real time using gamepads. For most teams, Teleop is where the majority of programming effort and driver practice time is invested because it is the longest phase of the match and it directly determines competitive performance. In the FTC, the teleop mode control is being run for 2 minutes after the autonomous run. So what is the teleop control and why is it matters? Teleop in FTC is the game mode where the driver manually operates the robot using a gamepad, with the robot responding a real time to every input the driver makes. Excuse me. In competition, teleop follows the 30-second autonomous period and lasts approximately 2 minutes. So after autonomous 30-second autonomous, it will transition to teleop mode for 2 minutes, making the majority of each match by time. Teleop code is structured as a loop. The code executes the same block of instructions continuously many times per second, and each iteration reads the current state of the gamepad and updates motor and servo outputs accordingly. This looping this looping architecture is what makes the robot feels responsive. Every time the code loops, it samples the latest joystick position and immediately applies the corresponding power value to the motors. The quality of the teleop code has a direct, measurable effect on driver performance. Poorly structured teleop code introduces control lag. The robot responds late to the inputs. It creates dead zones, ranges of stick positions where the robot does not move. It produces a jerky behavior. Motor jumping abruptly between speed values. Good teleop code feels transparent. The robot moves exactly when how the driver intends. As a coach, your role in teleop development is to help students think from the driver's perspective rather than purely from the programmer's perspective. When reviewing teleop code, ask what does the driver need to do the most frequently. That action should be the easiest to execute. What actions require precision? Those should have reduced sensitivity or the dedicated fine control mode. What happens if the driver accidentally pressed the wrong button during the tense match moment? Designing for error recovery is as important as designing for normal operation. Teleop also produces a rich educational environment beyond the programming skills itself. Students who iterate on a teleop code to improve its feel encounter concepts like input smoothing, deadband implementation, and control sensitivity are real control engineering concepts through the hands-on immediate feedback loop. So there are two types of drive control paradigms used in FTC, each with different characteristics that suit different drivers and strategies. Let's examine both so coaches can make an informed recommendations for their teams. Tank drive uses a one joystick per side of the drivetrain. The left stick controls the left motor and the right stick controls the right motor independently. Push both sticks forward and the robot moves forward. Pull both back and it reverses. Push the left stick forward while the right stick stays neutral. The robot pivots left around the top right wheel. The one-to-one mapping between controller and the wheels is conceptually simple and easy to understand, making it the natural starting point for our new programmers and the new drivers. The challenge with tank drivers is execution. Driving perfectly straight requires both sticks to the push to exactly the same direction simultaneously, which is harder than it sounds over a 2-minute match. Arcade drive use a different paradigm. One axis, usually the left stick's vertical controls forward and backward speed. Another axis, usually the right stick's horizontal or the left stick's horizontal controls turning. The code internally combines these two inputs into individual motor power values through a mathematical formula. Many drivers find this more intuitive for straight line driving because they only need to manage one axis to drive forward. The robot tends to hold a straight line more naturally. For starter robot, the initial teleop program uses tank drive. This is the right choice for new teams because tank drive code is simpler to read and understand, which makes it easier to debug and easier to teach. As students become more confident, they may naturally want to experiment with arcade drive, encourage that experimentation. Some experienced team develop hybrid schemes using one mode or normal operation and other for precision tasks. The most important point, regardless of the control scheme, driver practice matters enormously. A driver who has spent 20 hours practice with tank drive will outperform the driver who spent 2 hours with more sophisticated arcade drive setup. Prioritize practice time in early season. So we have a common control reference. This table maps gamepad's inputs to robot's action for basic drive function. Left stick forward moves the robot forward, left stick backwards move it backwards. When the right stick left turns to the robot stick left, it turns to the robot left. Right stick right turns it right. These four inputs covers all the drivetrain locomotion in a tank drive configuration. When this table abstracts away, but what our students will encounter immediately in the code is the joystick value convention. In FTC, excuse me, every joystick axis returns a floating point value of negative 1.0 and 1.0. The center rest position is 0.0. Pushing the left stick fully forward returns a value of negative 1 on the y-axis, not positive 1.0. This inverted convention surprised nearly every new student. It is a remnant of how Android reads gamepad hardware, and it is why teleop code that uses the joystick Y value directly, without negating it, drives the robot backwards when the student pushes forward. Understanding this convention is essential before students write their first teleop code. For full starter robots, students will also need to map the flywheel and feed servos. The R1 shoulder button activates the flywheel motor, the D-pad controls the feed servos. Planning the complete control mapping on paper before writing any code is a practice that produces dramatically cleaner and more intentional programs, and it gives the drive team an opportunity to provide input on the layout before it is locked into code. A controller mapping diagram, a simple sketch of a gamepad, documented for every practice session. The new drivers cannot be expected to memorize the full control scheme immediately. A printed reference card solves this problem. So this is the example of the tank drive example. So for example, the left motor set power to the negative gamepad 1 left stick Y and the negative gamepad 1 right stick Y. So the explanation is the left motor controls the left motor, the right joystick controls the right motor. If both sticks move forward, the robot will move forward. If the sticks, for example, the left joysticks is move forward and the right joysticks is move backward, the robot will turn to its place, or it will rotate. So this is the example of uh, a controller, official or allowed controller in an FTC. It is a Logitech controller, and I have a mapping guide for a tank drive. So left motor drive. So the left stick is for left motor, and the right stick is for right motor. Um, a tip, a great tip is to have a two controllers because you can connect two controllers in the FTC driver station app. So the first controller is for the drive only, for the driving of the robot of the FTC starter bot, and then the other controller is for the gates or the the servos, and the flywheel. So here's can you what I what I think the mapping for the second controller. So for the gates or the feed right and left servo, you can use the up, down, left, right arrows on the left side of the joystick or the gamepad, and then the R1 for the flywheel motor. So that way, two students can use the two gamepads, so that it would not cause a confusion when the competition or the match starts. So again, the first controller is the left motor drive, left motor for the and the right joystick for the right motor. So it should be a tank drive, and then the controls for the feed and right servo can be happen to another controller, so that it would not cause a confusion. Okay, so let's move on to the autonomous mode. Our fifth section is the autonomous mode. In FTC competition, autonomous is a 30-second period at the beginning of each match, where the robot operates entirely without a driver input, running on pre-programmed instruction. It is technically the most demanding aspects of FTC programming, and it is where the investments in good code quality most directly translate into competitive points. So, what is autonomous? Autonomous mode is exactly what the name says. The robot operates autonomously, or you just need to click the start button and you can completely lift your hands or fingers out of the robot so it starts automatically or autonomously. In here, the robot operates autonomously without any human input, executing a sequence of instructions written in advance by the programming team. The drive team initializes the autonomous program before the match starts signal fires, and from that moment the robot performs entirely on its own. No driver can help it, correct it, or intervene. The implications for the programming are significant, because there is no human in the loop to correct mistakes. Autonomous code must be precise and robust. The robot will do exactly what the code says, nothing more, nothing less. If the code says drive forward for 2 seconds and turn, the robot drives forward for 2 seconds and turn. If the floor surface changes, if the battery is slightly depleted, if the robot drifts slightly during the turn, those are real-world variations will affect the results, and only more testing and code refinement can address them. For a gaming strategy perspective, the code's autonomous period rewards teams that can execute specific scored actions reliably during those 30 seconds. Autonomous points often carry bonus multipliers or additional value that makes them disproportionately important to the final match score. And them a team that scores reliably in autonomous over a full competition day has a significant cumulative advantage. For coaches, the most important autonomous coaching principle is build incrementally and test each increment thoroughly. A new team's first autonomous goal should be achievable and consistent. Drive drive forward off the starting tile and stop. Then extend to drive forward into scoring zone and then add one score action. Each increment should be tested under multiple conditions: different battery levels, different starting positions, different floor surfaces, before the next increment is added. A simple, reliable autonomous routine scores more total points across a competition day than a complex, inconsistent one. So here's in this part, I have a GIF or GIF that shows an example of an autonomous where the human pushes a start button and the robot will move autonomously depending on the code that the programmer is coded. So how it works, the autonomous mode. So this flowchart shows the complete life cycle of an autonomous program, from writing the code to the robot executing it on the competition field. Let's walk through each stage. The first stage is writing the code. FTC teams can write autonomous programs using three different tools: Box, the visual block-based editor; Onboard Java, the text-based Java editor and runs in the browser on the Control Hub; or Android Studio, the professional Java development environment. So for this session, we learn how to use the blocks or the block-based editor. Blocks is the recommended starting point. As what I says, we use blocks for this live session. It removes syntax errors from the equation and lets students focus on the logic structure. Second stage is the SDK compilation and syntax checking. The FTC Software Development Kit automatically checks your code for errors when you save in blocks or when you build in Java environments. Errors are flagged before the code ever reaches the robot. This compile team checking is the critically safety feature. It prevents fundamentally broken code from being sent to the robot. The third stage is uploading to the control hub. In blocks, saving automatically uploads the code to the hub via Wi-Fi connection. In Android Studio or Onboard Java, in an explicit build and deploy step sends the compiled code to the hub over Wi-Fi or USB. The fourth stage is match start. The driver station sends the autonomous start signal. The control hub begins executing the selected up mode from the beginning of its run up mode method, reading and executing instructions sequentially. The fifth stage is the robot executing its routine, moving, scoring, and parking all without any driver input. When the autonomous period ends, the hub stops the program automatically. The phrase at the bottom of this slide is worth reading aloud and letting settle. The robot does not decide, it only follows code. There is no intelligence, no adaptation, no guessing, only precise execution of the programmer's instructions. When the robot does something unexpected, and autonomous, the cause is always in the code, teaching students to own that completely. To see unexpected robot behavior as a signal to look at the code, not to blame the hardware, is one of the most empowering coaching contributions you can make. So I have a example code here. Example example of what autonomous mode looks like. For a while. So this is a another type of competition, world skills, but it uses the same robotics component. It's a Studica, but I just wanted to show you what how the autonomous work. So the players or the contestants just push one button so that the instructions that the programmers is code and then translate it to the robot's movement. Okay, so that's the example of the autonomous mode. So let me just explain what happened in the video, we can, or I can just explain it. So noticeably, so the video link here provides the real-world view of the functional autonomous routine looks like in the practice. Noticeably, notice the deliberate pacing. The robot does not rush. Each movement is clean and deliberate. Forward movement stops completely before the turn begins. The turn is executed to a specific position, and the next movement starts from a known stable state. That measured pacing is deliberate programming choice that sacrifices raw speed for reliability. A routine that completes every action predictably is worth more than a full competition day than a faster routine that occasionally misses a target or ends in an unexpected position. Also notice the absence of any correction. The robot does not adjust, re-aim, or respond to anything in its environment. It simply executes its sequence. If it drifts slightly during a forward drive, it continues with that drift. The only way to improve the accuracy of this routine is to go back to the code, adjust timing or power values, again, and iterate. That cycle of observe, adjust, test, observe is the engineering process of miniature. So let's move on to the last or the fifth final section of the basic of of this session, the block coding for robot control. It is the basic robot movements. This section grounds everything we have discussed about programming in the physical mechanics of how motors produce motion. A programmer who understands these mechanics can predict what their code will make the robot do before running it, and that predictive ability dramatically accelerates an iteration cycle. So, basic robot movements are the fundamental directions a two-motor differential drive robot can perform. There are five: forward, backward, left turn, right turn, and pivot turning. Forward and backward are the simplest. Both motors spin in the same direction at the same speed. The robot translates without rotating. Forward forward means both motors in the positive direction. Backward means both motors in the negative direction. Left turn and right turn are achieved by driving one side faster than the other, or by stopping one side entirely. When the left motor slows down or stops at and the right motor continues, the robot arcs or pivots to the left. The degree of curvature depends on the speed differential. Pivot turning is a special case of turning both motor spins equal speed in the opposite directions. For example, the left motor moves forward and the right motor moves backward. The robot rotates around its center point without translating. It is the fastest way to change direction, and it produces the most consistent, repeatable turns in autonomous programming. So, for coaches, teachers, students, teaching students to plan their autonomous routine in terms of these five building blocks before opening the blocks editor is one of the highest leverage practices you can introduce. A student who writes on paper, drive forward for 1 second, pivot left for 0.8 seconds, drive forward for 0.5 seconds before writing any code will write that code faster, with fewer errors, and with better understanding of what each block is supposed to accomplish. So, how motors control movement commonly in FTC, and commonly both motors should be positives to move forward. But in starterbot Studica Rev, the other motor or the right motor, either way, is supposed to be negative so that it can move forward or backward. and in turn left, you just need to put you can use pivot point or turn left or right using a for example, you need to stop the right motor and then move the left motor to turn right, or you can stop the left motor and you can move the right motor to turn to the left. Here's an example of a diagram or how the motors control movement. You can have a straight turn left, which means you need to stop the left motor and then you can move the right motor forward so that it would turn to the left because only the right motor is active. Also in the turn right, you can stop the right motor and then you can make the left motor move so that it will turn to the right. And the pivot turn is when you move the motors, or you can the both motors is active but it runs opposite. So meaning if the left, for example, the left motor is moving forward or the right motor is moving backward or vice versa. Yeah. Yeah. So the pivot turning, one motor stays still and the other motors moves. Then for the example code for the time forward movement, I'm just gonna explain what the code in this block code. So we have a function or a wrapper called to run up mode, and then the up mode name is practice autonomous. So I have created a variable called speed, and I set it to 0.5 or a 50% robot speed. And then I put a call wait for start so it doesn't automatically or immediately run the motors when I click the initial button on the FTC driver station app. So we have I set the motor 0, right motor 0, dot power to a positive speed of 0.5 and the left motor power to a negative 0.5 so that it moves forward. Then I call this sleep for a 1000 milliseconds so that the motors will run for 1 second, and then I put a set power again to 0 so that after 1 second the robot will completely stop. So here's an example of the move forward. So that is the example of I'm gonna play it again so that you could see because it happened so fast. Okay. And then for another timed movement, so I created a code that would the robot run in a square shape. So I use the same code, but I also use a loop block. So it repeat 4 times on what inside the loop block. So it says repeat 4 times do, and then what's inside the loop block. So I put again the forward. So in starter bot and FTC, the other motor should be on the opposite so that it would move forward. For example, right motor 0 is in the positive speed and the left motor is in the negative speed. And then for the accurate movement, I put a time or call sleep for a 1000 milliseconds or 1 second, and then put a stop or a motor stop movement. So I put the 0 on both motors, and then another sleep to 1.3 seconds. And then here I created in this part I created a turn. So I only make the right motor move so that it could turn to the left, to the wait, oh yeah, and then left motor to 0 so that it would actually turn to the direction that you want to put, left or right. And then I put a 1.8 seconds so that it actually uh kind of turned into a 90 degrees uh, position, and then a stop again, and then it just repeated 4 times. So this is the example of it. So in this example, I use the left motor to move to the right because we have a limited space in here. So that is actually it. So that is actually it for this session. We began again, and with that we reach the close for today's session. Let me bring the major themes together before we leave our or well when after we wrap up this live session. So we began with the rev control hub, a single device that is the brain, motor controller, sensor interface, wireless communicator, and power manager of the FTC robot all at once. We learn how to configure that hardware through the Driver Station app, establishing the name to port mapping that connects physical components to mapping that connects physical components to software references. We installed the Rev hardware client, connect the hub wirelessly, and set up the programming environment. We analyzed tele-op code that maps joystick inputs to motor outputs in a continuous loop, and we decode 2 autonomous programs, 1 simple forward movement, and 1 complete square path, block by block. So again, I will share you the quote by first. We don't use kids to build robots, we use robots to build kids. So every concept we covered today, every block of code, every moment of troubleshooting for students will experience this season. All of it is in service of building the next generation of engineers, solvers, and collaborative thinkers. That is the real work of FTC coaching. Thank you for your time and dedication today, and I look forward to seeing you on our next live session. So for the last, I would also like to join you again, invite you again to join our last live session happening in May 23, naming application and competition practice. So in this last session, we have a code configuration, and then guided practice run, and then testing and debugging. So that's it, guys. Thank you, guys.
Challenge challenges kids ages 12 to 18 to program, design, build, and compete with robots.
First Tech Challenge is one of 3 engaging FIRST programs.
Every year they release a new challenge.
Once you get the challenge, you figure out your game plan.
Teams use a reusable kit to program robots in a variety of coding languages.
Every year you also learn more and more about coding, so then your code's gonna get better and better.
Personally, I do not learn hearing about it, but hands-on is just go into it. Instead of saying, oh, I know how to build this robot, I can say, I built this robot.
In First Tech Challenge, students are developing a broad range of skills.
Manufacturing, hardware, troubleshooting, but there's also a lot of things that you learn that you wouldn't necessarily think about. People skills.
Skills, helping one another, helping other teams.
The program draws so many students that come in who just want to do the marketing, who just want to do fundraising. And that's a great thing that the kids learn very early on.
The model of FIRST has provided incredible opportunities for the students to interact with professionals.
Whenever I asked my mentors a question, they always flipped the question around and asked, where would you find the answer to that question if I weren't here? They slowly built my confidence up so much more to a point where we weren't asking them questions, we were just going.
Each team has to compete at a local event, win awards at the local event, and then they're able to move on to the first championship.
You walk into the room and there's that smell. The smell of robots.
There's different languages, different culture. It's just the best thing ever.
There are scholarships for colleges, universities, as well as technical programs.
I think it's incredibly important for youth to see careers in science and engineering as a possibility for them.
First Tech Challenge is like an avenue for me to express my creativity with like-minded individuals that later become my friends through the program.
First in one word, wow.
Fun!
First is inspiration.
First is amazing.
First is hope.